Welcome to qnawire.
Hello everyone, this is the solution to problem 9 of chapter 24 of college physics. We're asked to find the current that's running in a loop of wire that has a resistance of 20 ohms and is perpendicular to a uniform magnetic field B that initially has a value of 10 to the minus 3 Tesla and decreases to 0 Tesla over a 30-second period. We are also told what the area of this loop is. And so all we have to do is use Faraday's law to find what the induced EMF is. And so using the fact that E is equal to I times R for an ohmic resistor, which we can assume this wire to be, we're going to work out that I is going to be equal to V over R, where V is actually going to be equal to the induced EMF over R. So then let's go ahead and find the induced EMF is. So epsilon is equal to minus n for number of loops times the change in flux, magnetic flux over time. But now we have that n is actually 1. So I'm just going to go ahead and put that here. N is equal to 1. We have one single loop of wire. And so we have that the flux is just the change in B times A. This is simple because the area vector that is coming out pointing normal to this loop is actually parallel to the magnetic field. Otherwise, there would be a cosine theta term factor here that would involve the angle between the area vector and the magnetic field. But here they're parallel, so that's fine. And divided by the time it takes for the change to occur. And so here, B, we're told that the A is the area. It does not change, and so A comes out. And so we just write this as a block, like a big change in B over a big amount of time. And so B goes from 10 to the minus 3 Tesla to 0 Tesla. So it's actually has a value of minus 10 to the minus 3 Tesla divided by dt. And so now just using this fact, we can write this into formula here. So these minuses cancel from the EMF. And so we have A times BF, so B final minus B initial. This is just the change in the magnetic field divided by the time it takes for the change to occur, all divided by R. So if you put all these values in here, then you end up with 3.3 times 10 to the minus 9 amperes, which is also known as 3.3 nanoamperes. So that is our